Yesterday we were looking at some applications of the derivative, the use of differentiation in some applications. And that was about, we briefly looked again at Taylor series. We saw some motivation, or, we saw some work that went some of the way towards justifying the form of the Taylor series, and why we do see the derivative of a function cropping up as the coefficients in the infinite polynomial expansion of a function. That is the Taylor series. So we saw that yesterday. We also saw the concept of the stationary points of a function, being able to classify these into local minimums, local maximums, and points of inflection, and so on. We saw an application of this to solving an optimization problem. Okay, we presented a problem of manufacturing a box out of certain materials which had different costs, and with a few requirements about the dimensions of the box and the volume that the box had to be, we were able to use the idea of stationary points to minimize the total cost of construction of the box. Okay, so that's what we did yesterday. You can see the video of yesterday's lecture and look at the visualizer pages from the Google Plus page as normal. And today we're going to look at another couple of applications. Okay, and then after today, I think all of the end of chapter exercises will be open up to you. We'll have done the necessary material for, so those can occupy us in the tutorials this week and next week and so on. Now there's many end of chapter exercises there, beginning on page 55, 56, 57, and 58. There's more than you're going to get through in the space of the tutorials. Okay, I've done that on purpose to give you plenty of work to do there, and you can find yet more practice questions and more worked examples if you look in the Schaum's Outline of Calculus book. Okay, that book which is linked to from, if you go look at the library block on the right hand side of the Moodle area, see here, Calculus. If you click through that, it clicks through the library website, and you can access an online version of that. There's a lot more material there as well. Sorry? They have paper. There's hard copies of it available in the library as well if you want to take those out as well. Yeah. I just kind of highlight the online version that's maybe the most accessible. It's a pretty cheap book to buy as well. All those Schaum's Outline books there, I think most of them sell for under £10. They're quite reasonably priced. Okay, so the two applications we're going to look at today are the two remaining ones, which is curve sketching and kinematics. Okay, so these are at the end of chapter 4. Now, curve sketching is this idea of going from the formula for a certain function, and typical examples we look at are going to be rational functions, which are quotients of polynomials. And using a number of considerations, being able to identify a number of key points about the function that will be sufficient for you to be able to sketch a graph of the curve. Now this is a little bit, this topic would have been far more important in the past, when we didn't have nice computerized tools available at our fingertips. So so to produce accurate graphs of functions, this would be very much the kind of procedure you go through. I still think it's a use, although we can easily type this formula into MATLAB, into your graphing calculator, into whatever kind of mathematical package you have. I think if you even type it into Google, if you even just type that into the Google search box, it's got enough enhancements on it that it just pops up a graph of the function straight away without you even asking for anything else. Despite having all those tools available to us, I think it still is useful to be able to do it by hand without a computer. Just because it gives you a number of ways to think about the function, and it's still important, I think, to have those skills and be able to interrogate the formulae and pick out interesting features about it, rather than just kind of offloading it to the computer all the time. Of course, in practice, when you encounter functions as you go through your career studying mathematics, of course, you just whack them into the computer straight away and you get the graph and you can start to look at it then. But I think it's still useful to have some ways to attack it without a computer as well. Okay, so that's what we're going to do for the moment. So we'll try and produce a sketch of the graph of this function, and then compare what we can deduce just by paper and pencil with an accurate plot of it from the computer. Okay, so we're going to take this function as an example. Now most of the details I think are all here, and these are a collection of things, collection of steps we're going to go through. So in no particular order, there's a number of items down here which are kind of the most important aspects of a function from the point of view of trying to sketch a plot of it. Okay, so you can see them here. First of all is to think about the domain of the function. Are there, now when you're dealing with these rational functions, are there any values which are kind of special, any values for which that function does not give a valid definition? So with rational functions like that, you'll be worried about zeros of the denominator. Okay, any location where the denominator is equal to 0 is going to be a place where the formula isn't well defined. Okay, so those will be important to know. And typically, as long as the numerator, if so, you can see here there's a problem with x equals minus a half. When x equals minus a half, the denominator is 0, and the numerator is not 0, it's just equal to some value. So that means as you get close to x equals minus a half, the function is going to be close to some particular constant divided by 0. So it's going to explode in value, either a very large positive value or very large negative value. So that's going to be important to think about for rendering a sketch of the function. So the second point, yeah, you want to accurate, or you want to appreciate how the function is behaving when you get close to those undefined points. And the function may have different behavior as you approach them from the left or from the right. We'll want to know where the function goes when it cuts the axes. So is the graph of the function crossing either the horizontal or the vertical axis, and if so, where? Asymptotes of the function. So asymptotes of the function are lines or other curves which our function we're looking at, which it approaches in a limiting sense. Okay, so it may be, when we're looking at this function f, as x gets very, very large towards plus infinity or towards minus infinity, it may be that there's some kind of limiting behavior of the function, that it's so some kind of limiting curve that the curve of f is going to approach. So those are called asymptotes. And then stationary points. So this is where the derivative is coming in explicitly. Are there any turning points in the function? Are there any local minimums and local maximums? And we'll want to render those into our sketch accurately. And then just kind of estimating, or just trying to put all this information together and avoid any kind of glaring mistakes in producing your sketch. So getting at least the right behavior, whether the function is positive or negative on various parts of the domain, and whether it's coming at these asymptotic curves from above or below, and so on. Okay. So we'll take this example function and we'll go through those items one by one. Okay. So first of all, as I've already said, this function is undefined, or this formula is undefined at x equals minus a half. Okay. So there's a problem there. So, and it is defined at all other values of x. There's no problem with that fraction at every other value of x. Okay. So there's one undefined point in the domain. So strictly speaking, the domain of the function is the real numbers except the number minus a half. So we can say the domain is R less the set containing minus a half. So how does f behave when you get close to this point? Well, if x is close to minus a half but to the left, so if it's slightly less than minus a half, well, you see, let's look at the numerator. As you get close to minus a half, the top gets close to 3/4 minus 7 minus 7. So the numerator is going to be negative. So the numerator is always negative when you're close to minus a half. Okay, but when you're close to minus a half on the left-hand side, the denominator, so when you're slightly less than minus a half, the denominator is negative also. Okay, it's 2 times something slightly less than minus a half plus 1 will still give you a negative answer. So when you're to the left of minus a half, you've got negative divided by negative, so overall you're positive. But when you're to the right of minus a half, when you've got a value of x like just ever so slightly larger than minus a half, okay, the numerator is still close to something quite negative, 3/4 minus 7, but the denominator is now positive. Okay, when you're something slightly greater than minus a half, multiply it by 2 and you add 1, you get something small but positive. So f is going to be some kind of constant, 3/4 minus 7, divided by something, something negative, 3/4 minus 7, divided by something slightly positive. So overall, f is going to be negative. Okay? So we can identify that to the left of minus a half, the function is positive and large, and to the right of minus a half, the function is negative and large in absolute value. Okay, so that's that second bullet point. Then we think about where it crosses the axes. So it crosses the x-axis, so you just evaluate the function, f at 0, you get minus 7. So that's fair enough. So it crosses the x-axis at minus 7. And if you look for solutions of f of x equal to 0, so you're looking for solutions of the numerator equal to 0, you see that that's because it's a quadratic, it's got 2 solutions, which is plus or minus the square root of 7/3. Okay? So setting the numerator equals to 0 gives you those 2 solutions. So that's where it crosses the x-axis, and it crosses the y-axis at the y value minus 7. Then the next thing we're going to consider is to look for asymptotes of this curve. Okay, so to find asymptotes of this curve, what we seek to do is rewrite the definition of f as some kind of curve plus a remainder part. And we want the remainder part to have the behavior that it converges to 0 as x goes to plus or minus infinity. Okay, so that's achieved there in that next line. So what's required to obtain this second expression here? This one here. Well, what we need to do for that is to take f of x, which is 3x squared minus 7 over 2x plus 1. And, well, there's various ways to think about this, but you're trying to divide the numerator by the denominator. So one way to think about it is you're trying to write the numerator 3x squared minus 7. You're trying to write it in terms of 2x plus 1. Well, to end up with 3x squared, you're going to have to multiply that by 3/2x, aren't you? So if you multiply it by 3/2x, then you do indeed get 3x squared. You also get plus 3/2x. Now there is no 3/2x in the numerator, so you're going to have to subtract that again. And there is this minus 7, which we haven't accounted for yet, so we need to put that in. And then you try and rewrite it again. You see you've got 3/2x times 2x plus 1. Now this part you try and write in terms of 2x plus 1. So what do you do to that in order to obtain minus 3/2x? Well, you have to multiply it by minus 3/4, don't you? If you multiply it by minus 3/4, you do indeed get minus 3/2x, but you also get minus 3/4, but we want minus 7. So if we've got minus 3/4 and we want minus 7, well, minus 7 is minus 28/4. If you've already got minus 3/4, you want to subtract another minus 25/4. So that's rewriting the numerator as much as we can using multiples of 2x plus 1. So this implies that when you form f of x, which is this numerator 3x squared minus 7 over 2x plus 1, we just get 3 over 2 times x minus 3/4 plus this remainder part, which is minus 25 over 4, all over 2x plus 1. Now this is nice because this bit goes to 0 as x goes to plus or minus infinity. So it's a constant over 2x plus 1. So this curve, which is a straight line, so it's a multiple of x minus a constant, this is an asymptote of f. Okay. So by doing this, we've been able to identify a straight line, 3 over 2, y equals 3 over 2x minus 3/4. And as x gets very large in the positive direction or the negative direction, f gets closer and closer in value to the value provided by this line. So that will have implications for producing our sketch. Now, how exactly does it get very close to this line? Well, you see, you can identify that as well. When x is very large in the positive direction, the error term, the remainder term here is going to be negative. Because it's something negative over something very large and positive. So as x goes to plus infinity, f is behaving like this line minus a small bit. That means the graph of f is going to approach that asymptote from below. Whereas when x goes very large in the negative direction, the error term here is something negative divided by something negative. So the error term is positive. So as x gets very large in the negative direction, f is looking like the value provided by this line plus an error term. So our sketch, the graph of f, is going to approach this asymptote from above. So by considering the sign of the remainder or the error term, as x goes to plus or minus infinity, you can determine whether f is going to approach that asymptote from above or from below. Okay, and you can feed that information into your sketch as well. Then we might look for stationary points of this function, but we find that there aren't any. When we differentiate the definition of f using the quotient rule, so we're applying the quotient rule to differentiate f there, we end up with this rational function, 6x squared plus 6x plus 14 over the square of 2x plus 1. Now to find stationary points, you're looking for zeros of that, zeros of the derivative. Well, that function, that rational function, is going to be equal to 0 when the numerator is equal to 6x squared plus 6x plus 14, but of course that is never 0. It's always positive. 6x squared plus 6x plus 14 is always going to be positive. You can confirm that by, well, it's positive for most values of x, and indeed the discriminant is negative, so it has no real roots. So it never crosses the x-axis. So the derivative is never 0, so there are no stationary points. So all this information that we've gathered, we could try and feed into drawing a sketch of the function. Okay. So our sketch would begin just with a set of axes. And we just look back at the various things we've identified. First of all, we identified this special value minus a half. So that's minus a half here. So the function was undefined at this point. And we decided that as x approached minus a half from the left, the function was getting large and positive. So that means the graph of the function is going to come down here, something like this. And as x approached minus a half from the right, we decided that the graph was negative. So the graph is approaching this asymptotic line from the at the bottom of the sketch. Right here, the graph is going to come up like this, okay? Because it's large negative absolute value when you approach minus a half on the right, and large positive value when you approach minus a half on the left. Then we had axis crossing points. We had it crossing the y-axis at about minus 7. And we had 2 points for crossing the x-axis at the square root of 7 over 3 and minus the square root of 7 over 3. This is approximately 1.5, approximately 1.5 minus 1.5. Then we had our asymptotic line. So the asymptotic line was this, the asymptotic curve was this 3 over 2x minus 3/4. So this is a line of slope 3 over 2, which goes through, which has intercept minus 3/4. So it's going to be some line roughly like this. So it's going to be minus 3/4, where it crosses the y-axis. So, and there's no stationary point, so there's no minimums or maximums. So we're not going to produce a turning point in our sketch of the graph at any point. Making this a bit. So this will go any further. So then it's kind of just a matter of kind of trying to join these dots in some kind of sensible way. Got these 2 points, and we're approaching this line asymptotically from below, and you're coming down. Go through that point and then approach that curve. So, I'm not asking for any compliments on my artistic skills here or anything, but you know, there's a number of features which I've, although not that pretty, but I have represented accurately some of the features of the function. Okay. So that's our attempt to sketch a graph of f. And you know, it's not that bad compared with the actual graph. So here, using Sage, I've plotted what the actual graph looks like, and the asymptotic line in red. Okay, I'm not a million miles away. This is more squashed in the vertical direction, so the curve looks more curvy because the y-axis has a lot bigger range in the y-axis. It's from minus 15 to 15. Mine is only going about half of that, from minus 7 to plus 7. Okay, so if you imagine mine squashed down, maybe it would look quite like that. Okay. So of course, in practice, when we encounter a function and we want to pick out interest, you know, we want to see its behavior, of course, we just come straight to the computer, and either using MATLAB or Sage or something equivalent, we can of course get nice views of it. Okay. But I still think it's useful to be able to look at the definition of a function, okay, such as this 3x squared minus 7 over 2x plus 1, and be able to pick out, to extract interesting features that its graph will have. Okay. Okay. Any questions about that, or any comments or clarifications you'd like on that? Okay. Okay. So you'll find a number of examples in the end of chapter exercises for you to try. The other application I wanted to discuss today was kinematics. And this is kind of, well, it's kind of think of this as an application of the derivative and integration and so on. So kinematics is a kind of simplified form of modeling the motion of objects. And we're not doing it, we're not studying in detail the forces acting on the object or looking in detail at the physics of it. Just some relatively simple tracking of the motion of objects in the presence of well, here I think most examples are going to look at is just motions of objects through a gravitational field, or with specified accelerations or velocities and so on. So really what we're doing is we're studying situations which feature these three quantities, x, b, and a. So x of t, and it's really just a one-dimensional analysis. So we're looking at objects moving in a straight line, or moving in that fixed direction. So if something's moving in a fixed direction, then really it's just moving through one dimension, and you can kind of track its position using just a one variable function, x of t. Okay? So t is the time variable, and x is giving you the one-dimensional position of the object along some direction. Then v is going to be its velocity, the rate of change of position, and a is going to be its acceleration, the rate of change of velocity. Of course, these rates of change immediately brings to mind differentiation. Okay? So we have this familiar idea that the velocity is the derivative of position, and acceleration is the derivative of velocity. Or equivalently, acceleration is the second derivative of position. Okay? So the acceleration at time t is the rate of change of velocity at time t, which is the second derivative of the position at time t. Now, there are, and you've probably seen before, there are a collection of equations. There are a collection of equations relating x, v, and a, and their initial values at time t equals 0. These are sometimes called the Suvat equations, just after the variables used. I can't remember all these equations, and I wouldn't actually recommend you memorizing them. What I'd recommend memorizing is just this basic principle, that acceleration is the derivative of velocity, velocity is the derivative of position. And everything else you can kind of derive on the fly from that. Okay. So we'll look at some initial questions based on this. These are in the notes in example 4.12. So we'll kind of rederive as needed any kind of equation linking these quantities, depending on the information we're given and depending on the information that we want to extract. Okay. So we'll look at this first question. A car is waiting at a traffic light, and the traffic light turns green. The car accelerates at a constant rate of acceleration, 6 meters per second for 4 seconds. What will the velocity be after 4 seconds, and how far will the car travel? Okay. So some kind of one-dimensional problem. Here's the set of traffic lights. Here's the car waiting at the traffic lights. So we'll say at time zero, you've got your car here, and we're told that it goes with constant acceleration of 6 meters per second. Okay, and we want to track this over the range t between 0 and 4. Well, this implies then that the velocity of the object at time t is going to be the integral of the acceleration at time t plus some constant. So the velocity at time t, well, the integral of the acceleration, the integral of the constant 6 is 6t, and we have our constant. Now this constant has a very particular meaning. This constant is in fact v of 0. Okay? If you put in t equals 0 here, you get that this constant c is v of 0. Now what is v of 0 in this situation? Well, the question tells us that the car is waiting at the traffic light. So at time equal to 0, when the traffic light turns green, it's not moving. It's got 0 velocity. So its initial velocity is 0. Okay, it starts moving due to its acceleration, but at time 0, it's got 0 initial velocity. Okay? So that tells us that v of t is 6t. And then the position at time t should be the integral of 6t. Okay? So the position is the integral of velocity. So this will integrate to, what will integrate to 3t squared, plus again another constant, And this time, of course, this constant is the initial position. When you put in t equals 0 here, you get that this constant is x of 0. And again, from the setup from the question and the way I've organized my scale, I've decided to call the starting position of the car x equals 0. Okay? So it actually has 0 initial position. At time 0, when the light turns green, the car is still there at the traffic light, so it's got position 0. Okay? So we have x of t equals 3t squared. And that will be enough to answer whatever question we're asked about. So what is it doing after 4 seconds? So the position at 4 seconds is x of 4. So it's 3 times 16, so it's 48 meters with velocity v of 4, which is 6 times 4, 24 meters per second. Okay, so it's quite a straightforward example. Number 2 is a bit more involved. Question number 2 pictures a student running to catch a bus. So students running to catch a bus, and the bus starts to pull away from the stop. At that moment, the student's 20 meters away and running at their top speed of 5 meters per second. And if the bus is accelerating at 2 meters per second, will the student catch the bus? That's the kind of classic kind of kinematics problem. Let's suppose it's one of these old-fashioned buses, like the London buses, where you can hop on at the back. Okay? So we've got to make some assumptions here. So we'll imagine this is the picture at t equals 0. And let's call this, well, so let's say that the bus, the back of the bus, the point the student is running for is located at position 0. So that means that the student is located at position minus 20. The student is going with, well, we're told they've reached their top speed. So they're running at 5 meters per second. And the bus is going to accelerate with a constant acceleration of 2 meters per second Assuming this is the positive direction of the x-axis, yeah, we've got negative 20 over here. So will this student catch the bus? Okay. Well, we'll use xs, vs, as for the student's values. xb, velocity b, acceleration b for the bus's values. Now, what do we want to say? We want to answer the question, will the student catch the bus? So the question is, will xs of t equal xb of t for any t greater than 0? Is there a time where the student will be at the back of the bus, ready to just leap onto it? Well, in order to answer that question, we'd want to get expressions for xs and xb. Now, we're told the student is running at their top speed, so they've got 0 acceleration, assuming they can maintain that top speed for at least a short amount of time. So the velocity of the student is 5 meters per second. So the position of the student at time t is going to be 5t. Well, you get position by integrating velocity. So you integrate 5 and you get 5t plus the constant. remember, like in the previous example, that constant of integration is the student's initial position. So the student's initial position is minus 20 meters away from the bus. So we've got a precise description of the student's location. And we get one for the bus's location. So the acceleration of the bus is 2 meters per second. So the velocity of the bus is 2 times t plus initial velocity, the velocity of the bus at time 0. What's the velocity of the bus at time 0? Well, we're told it's pulling away from the bus stop. So time 0 is the moment at which the bus leaves the bus stop. So it's got 0 initial velocity. So the position of the bus at time t is t squared plus a constant plus its initial position, but we've decided at the modeling we're going to say the initial position is 0. So the position of the bus at time t is simply t squared. So the question becomes, will 5t minus 20, will this ever equal t squared for any t bigger than 0? So that's equivalent to asking, will this quadratic equal 0 for any t bigger than 0? This is the question. Okay, well, we know how to answer that kind of question. Is a quadratic ever equal to 0? You can just check the discriminant. But the discriminant here is negative. Discriminant is b squared minus 4ac, so that's 25 minus 80. So it's certainly negative. So there's no solutions. Oh, question mark. Exclamation. So there's no solution. So student misses the bus. We could ask the question, could any student have caught that bus? Well, obviously they'd have to run quicker. If they could run quicker, they could have caught the bus. But is there any chance a typical student, is there any possibility someone could have caught that bus? Well, we could try and answer that question. So for that question, so there we're asking, i.e., what's the smallest velocity? The smallest velocity the student to give a non-negative discriminant. Okay, because the first time that there'll be solutions to this equation is the first time that this discriminant becomes non-negative. Now this discriminant, how did this arise? Well, the 20 came from the initial position of the student relative to the bus stopper, so we're going to keep that the same. But this 5 here is from the initial velocity of the student. Okay? So, i.e. the question is, when is minus vs squared minus 80, when is that equal to 0? Well, that's easy to solve. This implies that the velocity of the student has to be the square root of 80, which is 2 times the square root of 20. And this is approximately 8.94 meters per second. But this velocity, 8.94 meters per second, this is the velocity this velocity would cover 100 meters in, calculated, about 11.18 seconds.
That's the same bullshit.
Sorry?
That's the same bullshit.
That's the Usain Bolt. Well, it's not. Well, yeah, yes. Someone near to Usain Bolt. It's not easy. But can anybody do 100 meters in that time here? I mean, it's not out of the question. Does anybody know their 100-meter time? Okay. Okay, so what I've tried to do there is just to give, with yesterday's lecture and today's lecture, is just to give you a quick show of lots of different places where we applied the derivative and integration, and lots of different contexts in which it can be useful. So we had the Taylor series yesterday, the stationary points optimization problems. You've got the simple kinematics problems and the idea of curve sketching, or try to extracting pertinent information about a graph of a curve just from the expression, from the formula. So you see in the end of chapter exercises, there's loads of these exercises. This one, question 9, the first optimization one there, I kind of like this question. So this question is talking about an athletics field. So what athletics fields are roughly, you've got some central rectangular field, and you've got curved ends. You can have a curved running track around the field. Now, proper athletics tracks are 400 meters around the perimeter, aren't they? So 400 meters is one lap. So that's a constraint. You want athletics tracks to be standard, so you can have standardized competitions and records and so on. So we need a perimeter of 400 meters, but we'd also like to maximize the space in the middle for all the field events, the jumping and the throwing and all that. Okay. So this question, if you have this constraint that the perimeter has to be 400, you want a rectangle with two semicircular ends. What dimensions should you build it to maximize the internal area of the field, of the rectangular field? So determine the maximum possible area of the rectangular part of the field if you want your running track to have a perimeter 400 meters. I think you get an answer out of that. I think that roughly corresponds to how these things are built, so it's quite nice. The other thing to find is, so you're all aware of like a typical can of beans, the typical size of a tin can or a can of Coke or something. So this is related to that. It talks about a cylindrical food tin which is required to have a volume of 330 milliliters. Now, one of the main considerations in deciding exactly what shape to build that can is you want it to contain a certain volume, but you'd want to build it efficiently. So use the least amount of tin or aluminium in making it. Okay. So what kind of dimensions minimize the total surface area for a cylindrical tin if the volume is required to be held fixed? Again, the answer you get out of that is pretty accurate to the actual size of these things. But it's not the only consideration. You want it to fit nicely in the hand and so on, and other considerations. Those are some nice problems. Then there's some more graph sketching problems there for you to look at. More graph sketching. Then there's Taylor series problems. I'm manipulating Taylor series. Then we got kinematics problems. And then lastly, stuck at the end from 22 on, another bunch of optimization problems. Okay, so there's plenty of exercises there for you to be working on and exercising yourself with these applications. Okay. So next week we might do a quick spot of revision in one of the sessions, or maybe the tutorials for the upcoming test, and then we'll add the test the week afterwards as well. Okay.